Very happy to have Balu from Google Research talking about strategic learning. So let's welcome.
Thank you. Cool, yeah. Thanks for having me here. I'll be talking about a series of papers out in the past 7 or 8 years. It's topic of strategic learning. So I'll explain the setting, the basics, and some early results, and many open questions. Many of them are super crisp, and yet we don't even know the basics. Okay. So when you think about playing a game, you can broadly think about two types of agents for playing a game. One is the usual one that we have, the strategic agent, who is interested in his own utility. Like it's a rational, self-interested agent and plays to maximize the expected utility. That's how games are defined. That's how we reason about games. It's utility maximizing agents. On the other hand, it is very compelling to model economic agents as learning agents in light of computational and informational difficulties. So rather than thinking carefully about the rules of the game and seeing like what exactly gives me the maximum payoff, I might just use an off-the-shelf like learning algorithm to decide how to play. For example, I could use EXP3 to play in a game. Nothing wrong with it. And these algorithms come with some kind of low regret guarantee. With the increasing use of learning agents to play games, for example, certainly they are used in bidding. There is enough evidence now for this. Can we reason about these, like with learning agents playing games? What can they say about the setting? That's the broad setup stock. So what we understand quite well is when a game is played between all strategic players, right? Like the interaction between strategic players, that's exactly what game theory studies, right? The outcome is some kind of equilibrium, like Nash, for example. We know the existence results, like the computational hardness of the Nash and things like this. So we understand a great deal, like a whole bunch of refinements about equilibrium and so on. All this is known in the setting where strategic players are playing against strategic players, usual classic game theory setting. When you have learning agents all interacting against each other, the entire game is played just by learning agents. Even there, we understand a great deal, right? Like we know that if learners use some low regret algorithm, right? For example, then the time average strategies converge to coarse-correlated equilibrium. And similarly, they use like more sophisticated, like low swap regret algorithms. We'll go through these terms, but if you know them already, low swap regret algorithms and the time average strategies like converge to correlated equilibrium. We know something, actually. But what we don't know, or at least didn't know for a while, but even now there are a lot of open questions here. Thank you. A lot of open questions here is when you have strategic agents interacting with learning agents, right? Like, is it of any advantage to strategic agent knowing that the other guy is a learning agent? Like, what can I do about it? So that's the focus of this talk. In particular, not much is known. I think the laptop is frozen. Okay. Yeah, so this is the focus of this talk when strategic agents are interacting with learning agents. And in particular, even when a single learner is interacting with a single strategic agent, it's a two-player game. One of them is carefully thinking about their utilities and playing a utility maximizing strategy. The other of them is a learner. That's the focus of this talk. And even this was poorly understood, but I would say even now it is poorly understood. There are some very basic open questions here, including like what algorithm should the learner use and how should the strategic agent optimize, knowing the fact that the other agents. Okay. So just like very small slide on motivation, nothing much. Basically, like I already said, in auctions, like bidders are increasingly using learning algorithms to bid, and there's plenty of evidence for this. For example, this paper by Nikki Belong, Dennis and Tadosh, easy best paper 2015 talks about how bidders' behavior is like consistent with like them using new regret learning algorithm. The only difference is that it's not just the bidders are using, but the environment is neither stochastic nor adversarial, but it is just a platform which has its own interest in mind. So it could be adversarial sometimes, but it's not necessarily adversarial in its intent. Its intent is to maximize its own utility, for example, in this case, higher bid yield, higher revenue. So what should they do knowing the fact that the other guy is a learner? Right? So this inquiry was begun in a remarkable paper by Mark Berman, Jeanine Mao, John Schneider, and Weinberg, which is again a best paper award in EC 3 years later in EC 2018 on selling to a no regret buyer. Right? This initiated this line of inquiry. This talk can be seen for a good part as a strengthening and generalization of this results to general games. So this was an auction game, obviously, selling to a buyer in repeated auctions. So we're going to talk about like repeated normal form games. Okay, so what's the setup, right? Like, so you're having some game which is being repeatedly played, right? Like there's a optimizer with the devil here, and then there's a learner, and then something happens, and then like round two, they interact, like some other outcome, and so on, like T rounds happens. And we seek to understand like the long-term outcome of these repeated interactions between strategic agents and learners. Yeah. So what is no regret learning? I guess like most people will know here, but quickly just to recap, it's simply a notion that defines what it means to learn when you're making sequential decisions. At the end of T rounds, like how can you claim that actually you learned something out of the past interactions rather than just going through it? That's what this captures. Here's a bunch of like algorithms that you might have heard of. So the only difference between like regular learning and our setting is usually the learner interacts with an environment that has no preferences. But in this talk, the learner is interacting with an environment which has preferences because the other party is also playing the game who has utilities. So this is the formal setup, right? Like you have a set of actions that can be taken for the learner by the learner in each stage. That's set A. And then the learner's action at some stage T is little a sub T. And they accumulate a reward for playing action A, which is RT of A. And the learner is trying to minimize regret when compared to the single best action in hindsight, which is exactly what's captured by this single best action in hindsight. And this is their realized utility for whatever they play. Some of the T rounds. And simply an algorithm is no regret if this regret quantity is little of T. So that is the sense in which learning is happening because it vanishes if you divide by this T vanishes. So you are learning this time. Okay. So we'll go into next. If the learner is playing a no regret algorithm, what can you say about what can they achieve? So we'll start with a warm up result. So this is a paper in joint work with Yuan Deng and John Schneider. 7 years back, like we showed that the strategic optimizer, which is the other party, can guarantee themselves at least on the average the Stackelberg value of the game. V is the Stackelberg value of the game, regardless of the learner's algorithm. As long as they play no regret learning algorithm, that's enough. I don't need to know open the box of the learner's algorithm, how they play, etc. I can always get at least a Stackelberg value. So why is this interesting? So a quick detour on Stackelberg and Nash. Right? So what is Stackelberg value of a game? So this is a Nash equilibrium in this game, 1 and 1, because both agents are mutually best responding. So if I play up, you should play left. That's the best response. And if you play left, yeah, that's the best response. That's a Nash. But in Stackelberg equilibrium, it's a two-stage game rather than a simultaneous move game, and agents are mutually best responding, where the optimizer goes first, puts their foot down and says, this is what I'm playing. They're committing to a strategy, in this case down. And then obviously the other party will best respond to whatever the optimizer played. In this case, between 0 and 1, 1 is bigger, so the other party will play right. So down, comma, right is the Stackelberg outcome. So you can immediately note that the Stackelberg value of the optimizer is only going to be weakly larger. In this case, 2 is bigger than 1. 2. But for the obvious reason that like Nash has more conditions. Nash says that both parties are mutually best responding. In Stackelberg, only the second party is best responding. So the set you're optimizing over is bigger. So immediately it says, the previous result says that when you're playing against the learner, you're able to get Stackelberg, whereas if you play against a strategic agent, you'll only be able to get Nash. Right, so this is the transition. Okay, so that's the point. So the optimizer benefits if he knows that the other player is a no regret learner without knowing exactly what the algorithm is or anything. Just the fact that the other player is a learner already gives this benefit. And the proof is not very difficult, actually, so I'll quickly go through. The optimizer simply figures out in this game what is the Stackelberg strategy, which could be some mixer strategy. Then they keep on playing this mixer strategy over the T rounds, meaning they repeatedly sample from this mixer strategy over all the T rounds. Right? Any no regret learning algorithm will have to eventually learn to best respond. If they don't best respond, then it will lead to linear regret. That's by definition. So you will have to learn to best respond. And if you're playing action and you're best responding, that's exactly what is tackle for. So that's it. That's the proof. But there's a little more here. Crossing over, there is some nuance here, which is that what if there are multiple best responses, right? Like for I play an action, there are k different best responses. How do I make sure that you choose that best response, which is most favorable to me, which is as an optimizer? How do I do that? And there are ways to do it. Okay, so you mix your mixer strategy with like some other action with a tiny probability, and you ensure that you pretty much get the stack work very close to the stack. You can always do this in any game, as long as the learner doesn't have any weakly dominated strategy. So you eliminate all the weakly dominated strategies, take a game without that, then there's always doable. Okay, so, but that's a nuance. Okay, the point is, I can get Stackelberg value right away, knowing the learner. So the okay.
Sorry, so you're very rather and you're define some kind of optional or oracle to define the that. So the oracle is defined by whether a code or like the definition of code.
Their regret is just defined based on their own payoffs, independent of what the other guys are doing. I mean, the learner's regret is defined based on their own payoffs. Right? So they have the payoffs here. You repeatedly play this game and you get one of these like 4 different numbers and you accumulate these payoffs over capital T rounds. You go back, you fix the transcript of the play, and then you go back in this transcript. If you had regret, oh God, like I should have played this other single action, that is regret. Do you regret not having played any single other action? And if you play any algorithm which has low regret, then the optimizer is able to get stack control result, the warm-up result. But the next question is the optimizer's utility upper bounded by stack control? Like, can I get much bigger than this, or am I just bound to this with little o of t? Little o of t terms are always like ignored. So this is the second result, which is a characterization where the optimizer's utility is actually upper bounded by the Stackelberg value per round, if and only if right, the learner plays a no swap regret learning algorithm, which is a stronger notion than no regret. And if you get no swap regret or low swap regret, that immediately also implies like no regret, which is also called external regret. And intuitively, no swap regret simply says that the learner doesn't regret when he replaces all the time he played some action A with arbitrary another action pi of A or some arbitrary transformation function pi. So the usual example people give is whenever I bought IBM stock, like I could have bought Adobe stock, whatever. So basically this is swap regret. So whenever you played action A, you transform, and even then, like you have zero regret that like looking back, I did an arbitrary transformation action and I don't regret. If the learner plays no swap regret learning algorithm, then the optimizer simply cannot get more than Stackelberg value per. So formally, this is the definition, right? No regret. We saw that you're comparing yourself with the single best action in hindsight. So max over all the actions. Here you're comparing yourself with the single best transformation, right? So pi is a transformation, which is transforming your action 80 to pi of 80. And with the transformed action, I shouldn't be regretting the fact that I didn't play the transformed action. So that is still so do no swap regret algorithms exist, right? So we know that no regret algorithms exist, like EXP3, so on. But no swap regret algorithms they exist, but there's a very clever reduction by Gamal Mansour, which says given a no regret algorithm, how to get a no swap regret algorithm out of it. And this whole line of work also has started faster, papers on like getting faster no swap regret algorithms, which I won't go into, but this is the original work. Okay. So this result says that the optimizer's utility is upper bounded by Stackelberg if the learner uses the no swap regret algorithm. And here's the proof, which is again not very difficult, so I'll go through the proof. So let SA be the set of rounds where the learner plays some particular action A. Right? So you look at the transcript of the play, all the capital T rounds have gotten over. And in these rounds, like in some subset of rounds, the learner played action A. So let's call that set SA. And let's look at the mixed strategy alpha A, which is composed by a uniform combination of optimizer actions played over those rounds. This is there's like arbitrary number of rounds over which action A was played. Look at the mixed strategy for the optimizer, which is composed by exactly the optimizer actions over those rounds. Now, what does no swap regret mean? No swap regret is usually low swap regret, but let's say in this case, for simplicity, it literally meant zero swap regret. You had zero regret by swapping. It simply means that A is the best response for alpha sub A. That's exactly what this means. Whenever I played A, I don't regret playing like some other action B. So which means A is the best response for alpha A. So what this means is in the rounds of SA, optimizer's average payoff is at most the Stackelberg value. Because if I play something and the other party is best responding, then that's the Stackelberg setup. And the best such thing I can get is exactly the Stackelberg value. So basically, the set of learner actions is partitioning the T rounds into many such essays, depending on what the action learner played. For each action, there is a corresponding set essay. And with each essay obtaining a close Stackelberg. And that's it. So that means that you can't get more than Stackelberg if the optimizer is the learner is playing enough swap. This is clear. Okay. So there is a nice interplay between like a single shot game concept and the repeated game concept we're talking about here. So we are in a repeated game setting, and note that Stackelberg is a single shot game concept. We are relating the payoff of the optimizer repeatedly to the single shot game concept. Stackelberg, it is useful to mentally run this and see why the same argument fails for no external regret. After all, in no external regret also, I can say that, I can replace all my actions by a single best action, and I wouldn't like regret transforming my thing to a single best action. So it is, just think about it, like see why the proof fails. Okay, so far, the characterization says that if the learner is playing any no regret algorithm, I can always get Stackelberg. And on top of it, if they also have the guarantee that they have low swap regret algorithm, I cannot get anything more than Stackelberg, getting established. But what if not? What if they play some algorithm which is not no swap regret? Can I get more than Stackelberg? So for this, we'll define the notion of mean-based algorithms, which is again a concept defined in Mark, Jimmy, Matt, John's paper in AC 2018 that I spoke about, which initiated systematic inquiry, where mean-based algorithms are like the usual no-regret algorithms that you might have heard of, like EXP3 multiplicative weights, follow the perturbator, all such things, which simply says that I'm going to play the action that performed the best historically for the most part. With very high probability, I'll play this action. So formally, what it means is if I give you two actions whose payoffs are reasonably different, cumulative payoffs in the past are reasonably different, then you have to play with very high probability the action with the higher payoffs, which is natural. That's what this is. So it's a subclass of no regret learning algorithms. Not all no regret learning algorithms are this, but intuitively, if you think of no regret, this matches your. So if the learner is playing any mean-based algorithm, which is all these natural no regret, then it turns out that the optimizer is not bound at a Stackelberg value. Instead, the optimizer can get linearly more than a Stackelberg. Okay. So in particular, we'll use this game to illustrate this concept. So in this game, the Stackelberg value is simply 0. But the optimizer will end up getting linearly more than that. They'll get 2t. So why is the Stackelberg 0? Note that if the optimizer played down with a probability more than half, immediately the learner is going to play middle. Because left is anyway negative and right is 0. But if down has a higher probability than up, then middle is the best thing for the learner. But if I play down with a probability more than half, then down with the probability less than half, sorry, then I'm out of luck. This is the best thing that can happen. And then my utility is 0. So that's exactly what it is. Half up and half down, and the learner playing, the other guy playing right. Stackelberg value is 0. But in this game, we'll show how the optimizer is able to get 2t and not 0 times t, which is what the Stackelberg upper bound would predict. And here is why. Okay. The strategy is very simple. The optimizer is not doing anything fiendishly complicated. Very simple, and still manages to sort of like trick the learner. So you play up for the first half rounds, TO2 rounds. Right? The optimizer is playing up for the first TO2 rounds. And let's look at the cumulative utility for the 3 different actions of the learner, left, middle, and right. So Left is giving epsilon utility, which means as time passes, it's slowly increasing over time. Left. Middle is giving negative utility, which is the red one, so it is dropping quickly. And right is giving zero utility, so that remains flat. Then the next TO2 routes, the optimizer is going to play it down. We're going to switch. There's a single switch actions. And once I do this, the right, which is the yellow, didn't change. It used to be zero and now also it's zero. So it's always a flat line. Left, which used to be good, which used to give me epsilon, is now giving me -1. So left starts falling down. This. Right, which used to be terrible, actually, middle, which used to be terrible, giving me -1, is actually giving me 1 now. So middle starts to grow. But the real problem is that middle will not appear as a good action in the mind of the learner for a very, very long time. It will take linear time, basically until the end of the game. Right still appears as the best action in the learner's mind. And because of this, the optimizer is nicely cashing in, making the learner play right because of the hysteresis that is inherent to learning algorithms. It's decided that right is good, and it's very hard for it to change its mind. And you keep on cashing in this payoff of 2, which was impossible otherwise. And that's it. So you get a linearly more utility than stack doing this. And this is for all the algorithms like EXP3, duplicative weights, FTPL, like all these things that have this problem of cleverly exploiting the hysteresis inherent to these learning algorithms. Okay. So the takeaway is that the optimizer, when interacting with the learner, has non-trivial advantages. If the learner deploys like no regret algorithms, and in particular, if it is mean-based no regret algorithm, you can get clearly more, linearly more than Stackelberg. But if it is no swap regret algorithm, you can only get Stackelberg. But Stackelberg is still better than Nash, so already it's still better. Okay, so there is an immediate corollary here, which is that all mean-based algorithms have high swap regret. All these algorithms, EXP3, multiplicative waves, they should necessarily have high swap. The reason is that low swap regret algorithms are able to stop the optimizer stacking. They cap the optimizer. That's the result. And we know that mean-based algorithms don't. So basically, mean-based algorithms should have high swap. And it's interesting because it's too bad in some sense, because low swap regret algorithms are kind of unintuitive. They lack the simplicity of mean-based algorithms. And this result shows that this is kind of necessary. There's no way around it, that all mean-based algorithms are going to have high swap regret. There's a corollary of this characterization, which was interesting to us. But the question is low swap regret necessary? So basically, are there like high swap regret algorithms that stop the optimizer at stacker? Maybe it's not mean-based, maybe it's something else, but it can stop the optimizer at Stackelberg. Like, is that possible? Because we showed that for mean-based we can exploit, but maybe there's something else which can stop the optimizer. Is that possible? So the answer is no, right? Like in joint work with like Ishaq Mansour, Merer, and John Schneider, we showed that no swap regret is also necessary to stop the optimizer at Stackelberg. Meaning, if you give me any learning algorithm and you tell me that it has this high swap regret, I'll immediately be able to construct a game. It's constructible, where the optimizer's utility is exactly swap regret more than Stackelberg per round. There's a very deep coupling here, and swap regret is arising as a uniquely important measure to minimize in strategic interactions. So BT is what they can get, the optimizer can get, regardless of what the learner paid. And what this is saying is, if you end up like with the learning algorithm, the swap regret of S, then you will make the optimizer earn exactly a swap regret mode, meaning I can always construct a game which has this property. So therefore, if swap regret is linear in T, obviously this means like you're letting the optimizer earn linearly. So here's a proof of how you can construct a game which ensures that the optimizer is able to get exactly swap regret more, half of swap regret more than Stackelberg. So what do you have in hand? You have in hand a learning algorithm which has some swap regret S. By that, what we mean is we also have the entire transcript of play, and then let RT, right, be the instance. I mean, like the instance is basically T for like all capital T rounds, but little RT is the vector for round T, the learner payoffs for round T, which is yielding the swap regret of S, right, through some swap function pi. So pi is the signature for the fact that you get swap regret S. So you have this in hand. With this, I have to construct you a game and then tell you that in this game, I'm able to get as an optimizer swap regret more. And this is how the construction of the game is going to proceed. So the learner's payoffs are just going to mimic the RTs. That's not very surprising because I have a transcript which says this is the payoffs. Yes, I swap regret. So I'm going to copy exactly those RTs for payoffs in round T. For the optimizer, here's how I'm going to construct a game. We can simplify the game later, but for now, for intuition, it's very easy to think about constructing a game for an optimizer which has capital T actions. So the game is going to get played repeatedly for capital T rounds, but I'm going to say that the optimizer has capital T actions in this game. And what is yet to be done is filling in the payoffs for the optimizer for the capital T rounds. How do you compute the optimizer? And here's how we're going to do it. So the payoff of action little t for the optimizer is simply half times this. Half is for some normalization, you can ignore it. Is simply the swap, like the swap difference between playing like pi of j, right? We know that like pi is the signature which yields the swap regret S. So the pi of j and j. So this is the payoff of the optimizer for when they play action t against a learner who plays action j. This is how I'm going to define the payoffs in their game. Now, the nice thing about this is we simply said the learner is having a swap regret of S. What that means is if I add over all the capital T rounds, the difference between the swapped value and the real value, that's equal to S, which is exactly the optimizer payoff also multiplied by a half, which means the optimizer utility is simply half times S. This is by definition. Definition of swap regret. Swap regret says this difference when added up will yield S. So half of it is half of S. That's the optimizer utility. But now I have to show that in this construction, somehow I have managed that the Stackelberg values remain 0. Because I have to get linearly more than Stackelberg. This says I got S, which means Stackelberg should be 0 also in this construction, which also you can show. If you set payoffs like this, you can show that the Stackelberg value of such a game with the learner having these n actions, optimizer having capital T actions, set with payoff of action little t being like this, the Stackelberg value is 0. I can quickly say why, but check the paper for proof. So think about so what does it mean for Stackelberg to be 0? It just says that if I play a mixer strategy, then the learner is best responding for whatever the mixer strategy is, then I should not be able to get more than 0. That's the definition of Stackelberg being 0. Right? So think about you as an optimizer playing any mixer strategy alpha. Let us say that the learner best responded to the strategy with from action J. Let J be the response. Then what is your utility? Your utility is simply going to be you playing alpha and they playing J, which means like this is going to be like this, which is summed over like all the actions in your support of alpha, right? Of this quantity. Now, the fact that J is the best response for the learner simply means that this difference should be negative because J is the best response. So this difference, if this isn't negative, that's exactly my payoff. So my payoff is negative. As an optimizer, my payoff is negative. So which means my payoff is at most 0. The Stackelberg value cannot exceed 0. So that's how this construction manages both of those. The Stackelberg value is 0, and I'm able to get exactly swap regret more than the learner by using the swap function itself to compute my payoffs.
So why is there like a multiply by circle?
And so that is just like we want to keep like all the payoffs in like -1 and 1 everywhere. So this just like ensures that I take care of it. But that's not a big deal. You just forget about it. That doesn't do any weightlifting in the proof. Okay. So one question that you can ask is, it's a bit unsatisfying that there is a learning algorithm and then like you go and construct an arbitrary game yourself and then say that in this game, like, such and such happened. Uh, why is this allowed? This is actually not a problem because what is a game? Right? A game is simply a set of rules. But a learner is anyway ignoring the set of rules, right? Like they're not even looking at the game structure or anything. They are simply using past experience to play the game. So they are basically completely ignoring the optimizer payoffs. In other words, a learner you can imagine, and this indeed happens in bidding also, applying the same algorithm in a variety of settings. Like in bidding, like you can use similar things for like slightly different auctions where reserve prices are learned differently or the auction format is different. I could use the same learning algorithm. This point is saying that some of those games could turn out to be really suboptimal. So if I apply the same like swap regret, high swap regret algorithm, I can attack it with the game where it will yield like very high utility for optimists. Okay, so in some sense, like this result says we are stuck to swap regret. Is that really the case? That's the question. So are we stuck to low swap regret algorithms because they're somewhat non-intuitive? The answer is not if you're willing to use different algorithms for different games. Okay, so that result says only for a general class of games because I gave myself the power as an optimizer to construct a game, right? I am like looking at the payoff vector which generated high swap regret and then constructing a game. But if I have like a simple class of games which I like maybe auctions, like repeated auctions, maybe it is the case that like we don't need to use those operator algorithms, then that is indeed the case. So just to prove the point, like in this paper with like Rachitesh Kumar and John Schneider, 1.5 years ago, we showed that bidding algorithms, for example, in first price auctions, you could use like an online grading descent app. Okay, this is quite intuitive. It is known to have high swap rate. And nevertheless, it cannot be exploited in first price auctions, meaning that in this game, so what is happening in this repeated game, a bidder is playing repeatedly against an auctioneer who is the seller, and the seller's goal is obviously to maximize their own revenue out of this interaction. The bidder is playing, and in Mark's original paper, like EC18 paper, what they showed is that you can like easily exploit as a seller and get like more than Myerson's. Similarly, that's the goal for the seller here. Can I get more than 3 times Myerson's revenue, which is what like we should expect. What we show is that you cannot do it if I simply play this like OGD algorithm, even though it is high swap rate, right? Like you can show that the optimizer cannot earn more than Myerson's revenue. So sometimes like we have hopes for non-low swap rate algorithms, but it should be special class of games. If you want a sweeping result, like you're out of luck because I can always construct a game for like any player. Okay, so this is fine. I just gave you one simple game and then told you how to get better than the stackable value in this game. But in general, if you know that you're playing against a learner, what is the optimal gameplay optimized? Meaning like what sequence of action should I play to maximize my profit in the sequence of repeated interactions with the learner? If you're just happy with Stackelberg, that's very simple. You just play a Stackelberg strategy repeatedly for all the t rounds. But like you're not satisfied with that, you want to get linearly more than that. And what is the best gameplay? In the simple game, it was very simple. Like you played like one strategy for the first half of the rounds and the strategy for the next half of the rounds. There was a switch between up and down. It's good. But in general, what is optimal gameplay? So in this original paper, like with like Jon Deng and John Schneider, where we introduced this like general class of how to do it, we show that the optimizer's problem is a very crisp control problem in k dimensions, where k is the number of learner actions. Okay, so what's going on here is think of the k dimensional space of learners' cumulative utilities. I'm a learner, I have like 10 different actions. And all the time I'm thinking about like what is the cumulative utility that action 1 gave me, or the cumulative utility that action 2 gave me, and so on. So in my mind, I have this vector of utilities, cumulative utilities for all the 10 different actions. And every time the optimizer plays a new action, it is going to change the cumulative utility of each of my actions. Because against the optimizer's like new action, there is going to be a new utility for each of my actions. It is going to change the cumulative utility for all my actions. So the optimizer is making the learner walk in this k-dimensional space as they go, and they are collecting rewards as they go. And in this k-dimensional space, the learner is always going to play their action which has the highest cumulative utility. I have a vector, whichever element of the vector has the highest cumulative utility, I'm going to play that. It's almost like follow the leader. Of course, follow the leader has high regret, but what we show in this paper is that it's enough to assume that follow the leader is what the learner is playing, because we are going to look at mean-based learners here. And mean-based learners, like I said, is going to play the action with the highest utility with a very high probability. And now scratch off the high probability and save probability 1 in your mind, because that's simple. So then the problem is very crisp. You have an n k-dimensional space where k is the number of learner actions, and each action has some cumulative utility. And I am playing some actions as an optimizer, making the learner walk in the space of k-dimensional utilities. And as they go, they are transitioning from a region where action 1 was the best response to a region where action 2 was the best response, because cumulative utility of action 2 exceeded cumulative action 1. So how do I construct this walk of the learner in this k-dimensional space? That's the question. So the open question is, we showed that the optimizer can get v times t, which is the Stackelberg value times t. But what is the u star of g for any given game? The optimizer can get u star of g times t. It's game dependent, obviously. Just like the Stackelberg value is obviously game dependent. What we showed is u star of g is at least v of g. You can always get at least Stackelberg. But in general, what is u star of g? The interesting thing is we don't know of any finite time algorithm. It's nothing decidable for these questions. Meaning I give you a game. Okay, this is as simple as it can get. 2 players. Let's say 3 actions for the optimizer, 3 actions for the learner, or 2 actions for the optimizer, 3 actions for the learner. There's a matrix with 6 numbers. 6 pairs for the optimizer, 6 pairs for the learner. 12 numbers. Code these 12 numbers, just give it to you, and then ask. In this game, you know the Stackelberg value is blah. Say alpha. Can you get linearly more than Stackelberg or not in this game? We don't know of a finite time algorithm to decide this. In the limit, that's of course, like for any finite t, you can always compute a finite t, but in the limit, can you give me a finite time algorithm to decide between whether it's possible to exceed Stackelberg or not is open? So that's a sense in which like this area is full of open questions. Like this, we give this problem, and then the immediate thing to ask is, in this problem, what should the optimizer do? We don't know. Like in some special cases, we know, like in Mark's paper, like they said, like how to extract the whole surplus as revenue. That's an auction setting. In this special game that I showed you, I said like what to do. But in a general game, how to do this? Can you even decide in this game? Is this game exploitable or not? We don't know. Okay, so far, like we were in a setting which gave us like nice independence across all the rounds. Each action was, each round was independent of the next round. It was just a repeated play, and there was no bearing of the previous round of this round. But what if the optimizer or the learner or both of them had budgets? And that is in fact the reality, because actions have costs. It's not like actions are without costs. And I have a total budget in my pocket. There's a total amount of money I can spend, which means I'm linking across all the rounds. Right? If I play an expensive action too many times, I'm out of budget. I cannot play that action again. So that is the theoretical wrinkle here that the budgets are bringing, which is the nice isolation across rounds that we had in a non-budgeted setting is shattered in the presence of budgets. So what's the generalization of Stackelberg when I have budgeted settings? In non-budgeted setting, we simply said, I keep on playing the Stackelberg action. The learner will learn to best respond. That's the thing, like, if they didn't learn to best respond, then they have high regret. But when I have a budget, then the learner cannot even best respond to that particular action, because that action could like exhaust their budget for them. That's not even a feasible thing for them to do. Or even if the learner didn't have a budget, the fact that I have a budget as an optimizer raises some questions as to Stackelberg, the way we used to think about it as a single mixer strategy, repeatedly sampling from it the right motion, or are there other things? So we said that in the unbudgeted setting, the optimizer will never switch strategies, meaning they'll keep on sampling from the same mixer strategy if the learner has the ability to instantaneously best respond. Okay, so just to recall, here the optimizer mixer switched strategies, true, that's true. But they did it only because the learner has hysteresis, right? they took all this time to realize that this red middle action is the correct action for them to play. They are not instantaneously best responding, which is precisely what I'm exploiting as an optimizer. This game. The fact that if they were to instantaneously best respond, there is absolutely no point in switching like this from up to down. It has to play the same thing because they're always best responding. You figure out what is that action of yours for which their best response is giving you the highest utility, and you play that. That's it. But the interesting thing about the budgeted setting is this is something we showed a very recent joint work with Yanis Figueres and Eva Darosh, that in a budgeted setting, the optimizer will switch strategies even if the learner instantaneously best responds. Even if they have the capability to best respond, let's say within little of t rounds, or in this case, let's just say they instantaneously best respond. Even then, you will switch strategies and not play the same thing. Why is this the case? Here's a simple example. Okay, the paper with Yanis and Eva. Let's say the learner has zero budget. I mean, like learner has no budget. Sorry, learner has no budget. Therefore, all their payoffs, the cost for their actions are all zero. The optimizer has a cost only when they pay up and the learner plays left. It's a very simple payment structure. Everything else is zero cost. And then here are the utilities. Now, if I had infinite money in my pocket, I would simply keep on wanting to play up and let the learner play left because it's the best response for both of us. All is good, and then like we keep earning money. However, I only have a money of t over 2 in my pocket. T is the number of rounds, and in each round, if I pay $3, then in total I'll be paying 3t, whereas I only have t over $2, so I can't do this. Instead, you could play up for t over 6 rounds and down for 5t over 6 rounds, the remaining 5t over 6 rounds. The t over 6 rounds will exactly exhaust your budget. The remaining rounds you play down, so the learner plays this, and then you pay a cost of 0 because the cost is 0 here. And then you can get a utility of 4t over 3, which exceeds the utility from playing a fixed strategy. Now you could ask, maybe instead of playing this, I can mix between these two and play up with 1 over 6 probability and down with 5 over 6 probability. Maybe that does it. But the point is, if you play such a thing, the learner won't be best responding with what you want them to best respond. So
I had a question. I'm a little confused about the assumption or like the model. So it seems like here you're saying, look, the optimizer has utilities and the optimizer has a budget and the payments take out of the budget.
correct.
But if the optimizer can get away with putting in less payment, that doesn't impact their utility, right? So your utility is just looking at their payoffs in this utility matrix, not looking at how much they spend. So in a sense, you can spend
Excellent question. Okay, so you're asking like, why is utility not quasi-linear utility, which is value minus payment, right? This additive and separable dependence on money. And that's the motivation is coming from like lots of bidding products in the ad industry where like, for instance, there's a product which many companies like Google, Facebook, etc. offer called max conversions, where an advertiser says, here is $10,000, use it for the month of May, get me as many conversions as possible. And I don't care like how much money you have remaining for me at the end of this. Just give me as many conversions as you can. So that is like their interest. That's because like usually how these things work is advertisers have a monthly budget, which is allocated for this month. And if you have some money remaining, that's not going to come back for you at the beginning of the next month for the marketing team. This money is allocated for this. Use it to the best you can and maximize your value. So this is max value subject to the budget constraint or the ROI constraint. Sometimes like the way this is handled is there's an ROI constraint, which says like you give me at least so much cost per impression. There's another way to handle it. But good point, yes, that's why this is the case. So coming back here, there's a very good reason for the optimizer to switch now, because like I haven't run out of money, even though I really love to play this action for all the capital T rounds. I don't have the money. I play this for some number of rounds and then play down rounds. Even though the learner is capable of instantaneously best responding. And mixing these two to get out of switching, like I always play 1/6 this and down for 5/6, will not result in the best response from the learner that you expect. therefore you can't get pay off more than capital. So, okay. But the question is, okay, so can the learner instantaneously best respond? Like all this is predicated on the fact that you're getting 40 over 3. By doing this, I was expecting that when you played up 40 over 6 rounds, the learner learned to best respond at left. But then when you switch to down, they immediately switch to right, not hanging on to left for a long time, right? Like, can the learner instantaneously best respond? Not if you use a regular no regret algorithm, but there are algorithms, so-called no adaptive regret algorithms or no interval regret algorithms, which say that over any interval of time, I still get like sublinear regret. And there are such algorithms. If you use those algorithms, then they're not lazy. They can quickly switch. They can quickly adapt to the fact that the situation has changed and we have to best respond to this new world. Right? So they can instantaneously best respond. But this was the case where the learner did not have budgets. What if the learner also has budgets? Well, if the learner also has budgets, instantaneous best response is simply infeasible. Because like the best responding action could like actually exhaust my budget. So that's not even possible. But you could still ask, maybe for the whole game, like at the end of this whole game, look at the single best distribution of actions that I could have played, which respects my budget constraints, and I'm going to regret benchmark myself against the single best distribution of actions. There's a very nice paper by Molika et al., 2022, 4 years ago, which says that linear regret is simply inevitable for the learner and adversarial bandits with knapsacks. So this is simply a bandit with knapsack setting, multi-arm bandit setting, but knapsacks, meaning like you have cost, and then there's a budget, so it's like a knapsack constraint. And in stochastic bandits with knapsacks, such things are possible, but in advert, meaning sublinear regret is possible, but in adversarial bandits with knapsacks, this paper in Molika shows that you cannot get sublinear regret, meaning you can't even compete with a single best distribution in hindsight. So what is it? The best we can hope for is simply that the learner maximizes their utility in each phase, subject to spending their budget uniformly. Because I don't know what the future holds. So I should like keep uniformly pacing my budget because anything can happen in the future. I don't know how adversarially the optimizer is going to change. Who knows what the optimizer strategy is? So I will uniformly pace budget and maximize my utility. So what do we show in this paper? In repeated budget auctions, in particular repeated second price auctions. The setting is the following. So this is not a general game. So in this specific result, it's repeated second price auctions, but not between a seller and a buyer. The two parties, the optimizer and the learner, are both buyers. One of them is cleverly using the best possible utility maximizing strategy to participate in the auctions. The other of them is using a learning algorithm to participate in this. And then we are asking what happens when both of these guys have budgets, dollar amounts, because they're bidders, they have money, and they cannot spend more than so much money. They are, let's say, interacting repeatedly over the course of a day, week, or month. What will happen? The first thing we show is the multiplicative budget pacing. It simply means when my value is V, I'm going to bid V times lambda for some lambda. Less than 1. So I'm basically shading my value to make sure that I pace my budget. So this is called multiplicative budget pacing. And then I update my lambda as time goes. But this is multiplicative budget pacing. This strategy with the lambdas getting updated using a PID controller algorithm. Very simple, which simply says, hey, look, like I'm supposed to spend at this rate per round because this is my budget. What happened really in this round is I spent a little more than my budget. So maybe my bidding is too high. So I need to reduce my bids or reduce my lambdas. Or the other way around, that I'm spending too fast. What I spent is a little higher, or maybe I'm spending too slow, a little lower than my budget. Maybe I'm bidding too low, so I need to increase my bid, I increase lambdas. Using a very simple PID controller algorithm, where we just need the P controller, the proportional term, which just says I will increase my lambdas in proportion to the shortfall or the excess over the budget. Then see, and adjust my lambdas according to it. And what I'm going to bid is super simple: V times the lambda, my value V times the lambda is. And that algorithm actually ensures the learner will best respond fast enough, meaning in little of T round, you can best respond. And the important thing is we show the PID controller algorithm is robust. Much like we said that no swap regret algorithms are robust, that is, they will prevent the optimizer from earning more than the swap regret value. More than the Stackelberg value. we say that the generalization of Stackelberg, the budgeted Stackelberg equilibrium, where we said the optimizer can time multiplex across like different strategies. And let's call that the budgeted Stackelberg. The optimizer cannot earn more than budgeted Stackelberg against the PID control algorithm. And we also show that the time multiplexing is not hideously complicated. The optimizer need not keep on switching t times over the t rounds. It will switch exactly once. There are two phases, just two phases. And in general, if there are k budget constraints, we show that using an application of Carathéodory's theorem that there are at most k plus one distinct temporal phases for the optimizer. When k equal to 0, k plus 1 is 1. It just says there is one phase, which is exactly what we know in the usual Stackelberg setting. When there is like no budgets, k equal to 0 means 0 budget constraints. Then we know that optimizer is playing the same Stackelberg strategy repeatedly over the t rounds. So that's k plus 1 is 1. In general, you can have k plus 1 phases because they have one budget constraint here. Both have a single dollar budget constraint. Then 1 plus 1 is 2. We have at most two phases. Optimizer time multiplex plus 2. Yeah, so I'll conclude with some open questions. I guess I can reiterate the open questions. So basically, the interaction between learners and strategic optimizers in repeated games is beginning to be explored, and it has like, it has grown into a thriving area now with some entire sessions in EC on just on this topic. So what we saw is the optimizer can get at least Stackelberg value, which is already more than Nash, or weakly more than Nash, but in most games it is more than Nash. When the learner plays any no regret learning algorithm, no restrictions. And the optimizer cannot get more than Stackelberg if the learner plays no swap regret. That's an if and only if. But if you play off the shelf like no regret, things which you know of like EXPT, multiplicative weights, and so on, you will exceed Stackelberg. You can easily do it. And in special class of games like auctions, seller against buyer, buyer against buyer, bilateral trade, and so on, we are not bound to exclusively using no swap regret algorithms because the result that swap regret is necessary and sufficient, that if and only binding is only for general class of games. If you use special class of games, you have other algorithms to try, like on ingredient descent, for example, just high swap regret can still stop up for each time. Okay. So there's areas abounding with open questions, like many things are to be done. Like I said, even the very simple plain vanilla two-player setting, those are the 19 papers that I started with, we don't know the optimal gameplay for the optimizer. There's just like you're taking the learner through a controlled walk in an n-dimensional space, and you're collecting utilities and passes, and then as the cumulative utility vector changes, they are moving from responding with action A to action B, depending on which component of the cumulative utility is the highest. So it's very clean question, mathematically super crisp, clean, but we don't offer desirable algorithm to say, can you get more than Stackelberg or not, even for a very simple game. And then there are special classes of games for which you can ask, like, what are the algorithms beyond no swap regret or manipulable? I looked at a very specific setting of first price options and said, like, online gradient descent is fine. What about like other classes of games? Like study budgeted settings, like, and then like this talk is mostly focusing on normal games, like there's Bayesian games, extensive form games, and so on which also there's been like a lot of work. And then in general, for each of these games, like, there's a different form of regret. Like for Bayesian games and extensive form games, there's a notion of regret for profile swap regret. There's a question of like fast algorithms for profile swap regret, on which itself there's a separate stream of literature now. Fast algorithms for swap regret, in a bunch of papers and so on. I had the time to review all these things, but the message is that there's a bunch of like big open questions on like some fundamental things, not corner cases, like several things on. Yeah, that's it. Thank you.
Sorry, I missed it. Can you explain again what the learner is doing in the budget setting with PID?
Okay, so in the specific game that I'm studying is a repeated auction, repeated second price auction. Learner is trying to bid, right? So they have a budget in their hand, and then they are deciding like what to bid. I have a value VL as a learner in round T, let's say VL, comma T. Now, if I have a value VL, I'm always going to bid VL times some lambda T. That's it. That's what is called multiplicative pacing. And lambda T is the multiplier. And lambda T is moved up or down using a PID control. Meaning I'm going to say lambda t plus 1 is equal to lambda t plus some eta, which is the step size, that's the proportional term, eta times the error term, it's called. You are being proportional to the error. The error is basically the difference between the budget rate at which you should have spent and what you actually spent. Yeah, if you overspend, then you decrease the bid. If you underspend, you increase the bid.
What's the benchmark?
Oh, the benchmark the runner is competing against is the best bidding strategy they could have used.
So the best lambda that then.
So you're like, suppose you're subject to your budget constraint. And there is no price for like leaving a lot of money on the table. It's okay if you use all the money, that's fine. But tell me the best bidding strategy which would have optimized your utility subjective. And you compute your cumulative utility against this lambda based algorithm. Do you get like sublinear regret or not? Is what they are doing. And what we are saying is this PID controller algorithm is not just getting the regret, but more importantly, from the optimizer's point of view, they prevent them from getting more than farmers.
The benchmark itself doesn't have any pace.
The benchmark doesn't have any pacing, like, because
Okay, but the
algorithm has, yeah. Because the benchmark is like it should be, like only cares about the fact that I have so much money in hand, I shouldn't exceed.
I think, yeah, we have a question. For the result about for all algorithms with swap progress, there exists a game. Do you happen to know if the same thing holds specifically for auctions?
No. No, we don't know how to construct like auction games like that. Like that construction is specifically, maybe you can try to use the idea there in the construction for auctions where like I look at the swap value, right? Like I'm basically saying like there is a signature which gives, there's a signature transformation function pi, which certifies the fact that the learner has a swap regret of S. And I'm using that signature pi to compute, to set or to design the optimizer utilities as RT of comma pi of j minus RT of j as optimizer utility. Maybe you can try doing like this for auctions, but I don't know like if it will pan out like in. So I don't know. Like in general, like we don't know such a result. This is only if I can do an arbitrary gaming in constructions.
Okay, if there aren't any other questions, then we can take the rest offline. Yeah.